Okay, we're up to 2-4, day one. Got my Rockford gear on, ready to go. Today, we're going to enter into this strange sort of thing called imaginary numbers. I remember being taught this way back when. I'm thinking, okay, as if numbers, real numbers, aren't not challenging enough. Now you're going to throw these numbers that don't even really exist at me? So let's get started. The imaginary number is represented by the letter I. Now, don't get that confused with a variable like x. X represents anything. The letter I actually represents a number. It's the square root of a -1, hence the name imaginary. Mathematically, it's impossible. Now, strangely, it's actually practical uses electrical engineering. Brother-in-law is an electrical engineer, and I asked him, like, hey, do you really ever come across this? And he said, yeah, it pops up in some formulas that they end up having to use to understand electricity. So let that kind of mess with you. We have to use numbers that don't exist to calculate truths about electricity that does exist. Plant that seed. All right, well, let's get down to some rules here because this is day one, but day one expects you to remember a whole bunch of rules from Algebra 1. So let's be careful with that. Let's look at this. Square root of 100, we know, is 10. Square root of 25 is 5. Square root of 4 is 2. Notice 10 equals 5 times 2. So guess what? This is telling us that it's okay to take a square root number and break it into the product of two other square root numbers. That's if we read this sentence left to right. But if we read this sentence the other direction, right to left, it also tells us a different rule. And you gotta know both of these rules are true. If I have two square roots and I multiply them, 25 times 4 gives me 100, it's okay to multiply square roots. Keep that in mind. Now, let's look at this, square root of 9. Okay, hopefully you know what this is. It's 3, but let's talk about why it's 3. This is a square root. We call these two perfect square roots because if the area of a square is 9, we talked about this before, and it's asking you what is the length of one side, we'd say 3. Now, yeah, all the sides are 3, but this problem is asking for one side of that square with area 9. All right, square root of 16. I'd say, okay, if the area of the square is 16, what's the length of one side? That would be 4 in this case, and that's why we say 4. Now, not to get strange with you, but this is slightly confusing because the square root of 16 could also be -4. Like, well, wait a minute, well, why did you only write a 4? If it's written like this, they only want what's called the principal root, the positive answer. So, with that in mind, the square root of 18. So, if I said, hey, this is 18, what's the length of one of these sides? You type that in your calculator, you're going to get something like 4.2, 4.3. But that's not how Algebra 2 wants you to handle something like this. Algebra 2 wants you to break it up into the product of 2. Just like we said over here, you can take the square root and break it up into the product of 2. And the first thing you're going to do is think, what's the largest perfect square root that goes into 18? Remember, our perfect square root starts with 1, then 4, then 9, then 16, and this list just keeps going and going and going and going. But what's the largest perfect square root that goes into 18? That'd be 9. How many times? 2. So I would say, hey, what's the square root of 9? Well, we just said it's 3. 3 square root of 2 would be my answer. Hopefully this is coming back to you. But let's practice another one. Square root of 50. What's the largest perfect square root from this list that goes into 50? That'd be 25, 2 times, which is 5 square root of 2, because the square root of 25 is 5. Square root of 2 just comes along for the ride. Now we got a problem. Square root of a -9 you were taught that that's like not possible. But then along comes imaginary numbers. Just like we took out a perfect square root to make these work, what we're going to do is we're going to take out something that goes into this, but it's different. We're going to take out the letter I, which is really the square root of a negative 1. And then negative 1 times what would give us negative 9? That'd be 9. Now notice, we went from this, which is 100% imaginary, we broke it up into parts. Now this is imaginary, and this is real. So look at that as like an improvement. Now it's 50% imaginary, 50% real, and we say, hey, what is that? Well, that's the letter I. So we're done with this. Now what's the square root of 9? 3. We don't leave our answer there. We'd say 3i. Now, yes, you could continue doing every problem like that, but after you've done a whole bunch of them, you just say, hey, I'm going to take the I out, and there we have it. So this represents the square root of a negative 1. It's the same thing. I just went with the letter I right away. And then what's the square root of 25? 5. And you put the I last, just like 5x, 5y. How about this one? My recommendation is, first thing you should do is take out the I, and then we look at the square root of 18. Is there more work to be done with the square root of 18? The answer is yes. Notice square root of 18, we have 9 and 2, so I'm going to bring that same math with me, but the I comes along for the ride. And then I look at this, I say, hey, the square root of 9 is 3. So that'd be 3i square root of 2. Now a lot of students write it 3 square root of 2i, and that's okay, but the problem is students start going like this. And that is not the same thing. That I is not supposed to be underneath the square root. The student didn't mean to put it there, but they did. So I don't recommend writing your answers like this, and neither does Algebra 2. They want you to have it like this, and then things will go well. All right, let me pause that, get a few more ideas on the board. Okay, a few more ideas. First of all, you're going to have problems now that say solve. Now, if you remember, I said the square root of 49 or the square root of 36, if it's written like this, they only want what's called the principal root. That's a fancy way of saying the positive answer. Now, something's going to change. Now they're going to say, oh, and by the way, when they write it like this, they're going to say simplify, but then all of a sudden the rules are going to change and they're going to say solve. When you see that, that's a trigger to find the positive root and the negative root. And I'm going to give you a little jingle to help you remember this. So x squared equals 49. Here we go. Bada boom, bada bing, do the right thing. And we say, okay, what's the square root of x squared? X. What's the square root of 49? 7, but there is a plus or minus in front of it. Now your book is going to ask you on a few problems to factor to solve these. Now I'm going to show you what they mean, but fortunately for you, I'm going to steer you away from that strategy, technique, because it's way more complex than it needs to be. I don't think it's worth our time, but is what they mean. Subtract 49 from both sides, subtract 49 from both sides. I get x squared minus 49 is 0. And then from a previous lesson, I'd recognize that as a difference of two squares. So x and x, one's plus, one's minus, the square root of 49 is 7 and negative 7. I'd look at this and I'd say, hey, negative 7. I'd look at this and I'd say 7. Now notice the amount of work that took. I get the same answers as I did here, but the bada boom, bada bing, do the right thing is your go-to, in my opinion. All right, now let's talk about this one. Well, if you've been listening, kind of thinking, okay, I like that bada boom, bada bing, do the right thing. Bada boom, bada bing, do the right thing. So I get x over here. Now watch this. Plus or minus. Remember, if I have an imaginary number, the first thing I've been asking you to do is take the I out. And then I say, hey, what's the square root of 49? 7. So my answer would end up being plus or minus 7i. This one has just an extra step to it. Bada boom, bada bing, do the right thing. Take the I out. Don't forget the plus or minus. Easy to do that. 9 to the 5th, 72. Am I done? No, because the square root of 72 can be written as 36 and 2. Now I've got this that turns into a 6. I've got the plus or minus and the I and the square root of 2. So here it comes, plus or minus 6I square root of 2. A lot more going on this one, but if you keep track of your parts, you should be okay. Now math is going to get easier. Don't you love when that happens? Remember adding like terms? We got 3x and negative 4x is negative 1x, and then 2y and 5y is 7y. Well, they're going to have you find like terms with the imaginary number I. So that's not a big deal. Treat it just like this. These parentheses, they come at you for some reason when they introduce imaginary numbers. You have to know when does it mean multiplication, when doesn't it? Because of that plus sign right there, these parentheses really don't mean anything. So you're just looking for like terms. 4 and 8 is 12. Negative 7i and 6i would be negative 1i, which you could write as 12 minus I. Either one of these is fine. And then they change the language on you just to see if you can hang. What is the difference? You know what that means? Subtract between this and this. So whatever comes second is what we're going to subtract. So it would really look like this. This is the math problem that they're asking us to calculate. Notice there's nothing in front of this parentheses. So it's like these don't even matter. But there is a minus in front of here, which is just like a negative 1. And then you distribute that through. So I would end up with 4 minus 7i minus 8 and then minus 6i. Now I just look for like terms. 4 minus 8 is negative 4. Negative 7i minus 6i is negative 13i. Now they do ask you to put your answers in a plus bi form. That just means put your imaginary stuff second, put your real number stuff first. So don't get thrown by the instructions. A couple more things. All right, last concept for 2-4 day 1. Here we go. Square root of 2 times the square root of 2, I said you can blend those or actually multiply them. So we get the square root of 4, which is 2. Square root of 3 times the square root of 3 is the square root of 9, which is 3. Now, one thing I tell my students is if you square a square root, the roots fly off. If you square a square root, the roots fly off. Now look at this, I times I. Isn't that just the square root of a negative 1 times the square root of a negative 1? And if we follow that rule that I've been talking about, if you square a square root, the roots fly off, we find out, whoops, the true formula that I squared equals negative 1. That is huge. Keep that in mind. There is a trick in here though, because if I actually multiply this stuff together, I'd get the square root of 1, which I think is 1. That is not correct, so be careful. If I square a square root, the roots fly off. You got to stick with that rule in the world of imaginary numbers. Now, let's take this into practical use. Distribute this, I get negative 6i. Distribute this, I get plus 18i squared. Now remember, I squared is a negative 1. So negative 6i plus 18 times negative 1, which is negative 6i minus 18. And then they'll probably want you to rearrange it like that. All right, more sample problems coming if that was throwing you for a little bit of a loop. Remember, I squared always equals negative 1. Okay?